want to talk to you guys is the take-home portion of your exam. I have not yet uploaded it because I am not quite finished writing it, but this is what I'm effectively looking at. So I am going to give you what is effectively a signal flow diagram, and it's going to be on the assignment sheet, okay? So on the left-hand side, we have an acceleration. The acceleration will be converted into a force by our proof mass. Any mechanical damping that occurs will generate a noise force that is going to be the square root of 4 kBT gamma, the damping coefficient, times the square root of the bandwidth. Our force is converted into a displacement by our spring. The spring will contribute some RMS noise displacement. So let's see, here we're at force, here we're at displacement. And then this is going to represent the sensitivity of our capacitor. Right. So now we are at a change in capacitance. And then this block right here represents our measurement circuit. So that we are effectively at our output voltage, but capacitors have some associated RMS noise voltage that is root kBT over C. I'm going to draw this out for you all pretty and all that kind of stuff, but effectively you're going to analyze the system from, tip to tail. The acceleration goes through all of the mechanical and electrical conversion processes into an output electrical signal that I'm going to have you guys calculate. So that's going through the signal chain in one direction. And then I'm going to have you guys calculate the input referred noise acceleration for the whole thing. So effectively referring everything to the left-hand side to give me a particular signal to noise ratio. Or actually what I'm intending to ask you is what is the minimum acceleration that this system can measure if you need a signal to noise ratio of X, okay? The microstructure that you're going to be dealing with is going to be something like this. So we have a large plate with comb fingers. Like so. Then we have our fingers up here. So this is a stationary thing. It's biased at some level. We also have comb down here. It'll be stationary and it'll be biased at ground. And so this middle structure here is where our output voltage is going to be taken. And our structure will be mounted to a mechanical suspension that is some number of guided beam springs connected in parallel. It's going to be made of polycrystalline silicon, which has a particular Young's modulus, and all that kind of good stuff. And so I'm expecting you guys to be able to calculate the mass, calculate the spring constant, calculate the sensitivity of the structure due to changes in its position. Just as a heads up, the expected direction of movement will be in the up and down direction. From the sensitivity, I expect you to be able to calculate the output voltage for this particular circuit. The measurement circuit is literally this thing right here. So this is just a single-ended ratiometric system. If the suspension moves up, the capacitor at the top gets larger because the area of overlap is increasing while the capacitance at the bottom gets smaller. So it is literally just single-ended ratiometric measurement where one capacitance gets larger, one capacitance gets smaller. You guys should be able to figure that out and calculate the output voltage. So does any of this seem like stuff we haven't covered? Let's start there, since this is the test over effectively the first half of the materials. Anything seems sketchy or inappropriate for what we've learned in this class to this point? All right.
It seemed like a bit of a nitpick, but there's a lot of pieces put together here with no practice on, okay, how do we fit these in other than just piecewise kind of breaking it down. It's a little bit of an analysis paralysis problem.
But it literally is just piecewise figuring out each piece. And then I would argue that you do have practice referring things to the input of a multi-stage system because you had a homework problem on it. In that case, we were simply working with voltages, but it's the exact same principle. So each of these pieces represents the gain of a amplifier block. The gain of this first amplifier block is literally the mass. The gain of this amplifier block is 1 over the spring constant. The gain of this amplifier block over here is whatever the sensitivity is, and we talked about the sensitivity for structures. By the way, I'm being nice and giving you something with a linear sensitivity so that you're just going to get a rate and not a function that depends on displacement. And then this part over here is just going to be the conversion of the output signal, or excuse me, the conversion of effectively that displacement into, or the delta C into the output voltage. So I'm not trying to nitpick things here either, but it is literally just a step-by-step conversion process of referring it. You can convert your output voltage into a change in capacitance, which you can then convert into some displacement, which could be converted into a force, which could be converted into an acceleration by going from right to left, if that makes sense. Just like an acceleration can be converted all the way down to a output voltage by going from left to right. So I'm going to have you calculate what the RMS noise acceleration will be if all of the noises that I've indicated here, damping, spring noise, and capacitor noise, are correlated and uncorrelated, which is literally just you add them together or you sum the squares and take the square root kind of thing. So the purpose of this is to literally tie everything that we've covered together And for those of you that are working on your PhD and you're going to be using this class for it, expect something extremely similar like this, except not a capacitive accelerometer for your PhD qualifier question, if I'm writing it. So anything unreasonable? And I genuinely want your feedback. I don't want to set you guys up for failure, but I have looked at some of your first part of the tests and was a bit underwhelmed in cases. So I'm trying to give you something that is challenging, but straightforward enough to where if you put the time in, you should be able to get an answer that makes sense.
I would suggest that if we can get a class like suggestion, like for a small part of it, if you can show us how to begin with that instead of doing with the voltage which we already done in the assignment. We can go with similar kind of question with a small, like only the two of the beginning parts.
So, okay. Let's say, let's look particularly at our RMS noise force, right? So this is nothing more than 4 kBT gamma, which is our noise force spectral density caused by damping in our system. So this is Fn with a bar over it. And then we multiply it by our bandwidth, just like we did with thermal noise voltage, because we are converting a spectral density into an RMS value, right? So let's say, for the sake of argument, that gamma is 1 times 10 to the minus 9, and our bandwidth for the system is 1 kilohertz. Right? So using these numbers, we're going to have 4 kBT times 1 times 10 to the minus 9 times 1 kilohertz, which is going to look like 1 times 10 to the minus 6. All right, so let's see, kBT over Q would be millivolts. Sorry, I'm trying to figure out what the units are here, over here will be. Actually, we should want it in joules, right? Let me Google Boltzmann's constant in joules per Kelvin. .381 times 10 to the minus 23. Let's see. So kilogram meters squared per second squared times degree Kelvin. All right, so let me think about this. One times 10 to the minus 9, and then a 1,000 per second. What I'm thinking about right now is how the units are going to work out here. So we have mass times meter, mass times. Oh yeah, I totally forgot 300K. Thank you. 99% sure. Because, sorry, what, literally just having an issue with the units here.
I can suggest you can leave that part, but just like how to implement the combination.
Right, well, so we would just refer it. So this noise would give us an input referred acceleration that is literally FRMS divided by the mass. Because we've moved it over. That's it. So if we calculate, let's say, our RMS noise displacement, we would divide it by 1/k times the mass to get it, just like we did with the voltage. And I think technically with the voltages, we did it referring the squares back, right? So do the same thing. So square the force, divide it by that gain. So the force squared divided by the mass squared is going to give us the acceleration squared. Take the square root. The displacement here, the noise displacement here squared, multiplied by the gain, or excuse me, divided by the gain of this stage squared times the gain of this stage squared is going to give us the acceleration squared at the input, just like it did in the homework problem. It's literally the same process. Okay. All right, so that is what your test is going to be. I'm happy to answer questions and all that kind of stuff once I give it to you as well. Like, I'm not going to solve it or anything like that, but if you have any further questions, I'm happy to answer them. We do have a lecture to cover today, piezoelectric actuation, so let's get cracking on that. So piezoelectric actuation uses the inverse piezoelectric effect. Okay, so effectively that means we are generating mechanical deformations due to the application of an electrical field. So the constituent equation that describes that is mechanical stress measured in pascals is equal to Young's modulus also measured, in pascals times strain, which is a dimensionless quantity, minus our piezo electric coefficient, which is measured in coulombs per meter squared, times our electric field, measured in volts, per meter. Okay. We already had this equation when we did piezoelectric sensing. We're just using this one instead of the one that we used in sensing. Okay. So in general, we're going to find out that these placements that are induced by piezoelectric actuation are typically small for reasonable voltages. Okay. That being said, even though we get small displacements, there are several reasons why we might want to use a piezoelectric actuation scheme. So the advantages of piezoelectric actuation, the first one is that the actuation does not consume DC power. Okay. The second advantage is that the force that's generated, and that says forge, not force, excuse me. Force generated during actuation is instantaneous. So we're going to see when we talk about things like thermal actuation and all that kind of stuff, that since it takes time to transfer heat and all that kind of jazz, it's going to take time to generate those forces. Where with a piezoelectric actuator, if we apply the voltage, we get the force. And lastly, the forces generated can be large on the scale of multiple newtons, not micronewtons or millinewtons, newtons of force with these actuators, okay? So piezoelectric actuation is used in multiple current commercial devices. Piezoelectric actuation is how inkjet printers function. The piezoelectric actuation squeezes micro drops of ink out of the printer cartridge and propels them through the print head. As I mentioned the last time that we were talking about anything related to piezoelectricity, piezoelectric actuation is also part of most of our digital watches, computers, and all of that kind of stuff, because a quartz crystal resonator is an example of a piezoelectric actuator. We're applying a voltage at a particular frequency to generate mechanical deformation at a particular frequency that is used as a clock reference circuit. Okay. Another place that piezoelectric actuation is used is in biomedical sensing applications. Piezoelectric actuators can be used to generate surface acoustic waves. So you use a capacitive comb drive structure integrated on a piezo material to generate a surface acoustic wave, and then a piezoresistive sensor picks up the surface acoustic wave at the other end of its transmission and converts that wave back into an electrical signal. This is used in a lot of flow meters and things like that. So we are going to look at longitudinal and transverse transducers, much like we did when we were looking at piezoelectric sensing. So let's say that our longitudinal actuator is going to look something like this. So we have a plate. So these are our electrodes. Our piezo material is sandwiched between our electrodes. In this case, our material has a height of h. If we apply an electric field, so let's say that our electric field is in this direction, which we'll call the 3 directions, we should generate some force. In the 3 direction. We're going to talk about that force and all that kind of stuff here momentarily. And just to identify things, this is our A3 surface, and this is our A1 surface. So on the left-hand side here, we have a longitudinal actuator. I'm going to draw a transverse actuator over here on the right. It's effectively going to be the exact same thing, except that now our deformation is going to occur along the length of the actuator. So in the 1 direction. Our field will still be applied between our 2 electrodes, like so. But our forces will be generated in the 1 direction. This is still A3. This is still A1. All right, so let's look at longitudinal actuation first. So our constituent equation that is going to relate our mechanical stress and our electrical stress is T3 will be equal to E times S3 minus lowercase e33 times fancy script E3. So many E's in this equation, it's ridiculous, okay? So effectively, stress is equal to mechanical strain minus electrical strain. Right? So what if we allow our transducer here to freely deform? Pardon, what? Right, no stress. So T will be equal to 0, okay? So if our transducer can freely deform, then T3 will be equal to 0. And as a result of this, our mechanical strain or mechanical stress total, must be equal to the electrical contribution. Okay. So we can rearrange this. Say that our strain, which will be induced due to the application of an electric field, will be E33 times our electric field strength in the 3 direction divided by our Young's modulus. Well, our electric field strength is nothing more than our applied voltage divided by the thickness of our actuator. Where V is the voltage applied. If our strain is uniform, we'll have S3 is simply the change in H over H, which will be equal to E33 over EH times V. And from here, we can see that our induced displacement, which is just the change in H, is simply our piezoelectric coefficient divided by our Young's modulus times our applied voltage. Now, this is a very interesting result. It does make some assumptions here, the biggest one being that the strain, or excuse me, the stress is a constant. But the displacement that is induced in this particular configuration is independent of the geometry of the actuator. It depends only on the material of the actuator through its piezoelectric coefficient and its Young's modulus and the applied voltage. So effectively, if we have a material that's relatively easy to deform and we can apply a voltage across it, we can get a large displacement. Now, unfortunately, Young's modulus and the piezoelectric coefficient are tied together. So typically speaking, materials that have high piezoelectric coefficients also have high Young's moduluses. So we're not going to have anything to where we can just apply a small voltage and get a huge displacement. Okay. So let's look at a simple example here. PZT4. This is a piezoelectric ceramic. It's a man-made material. that is used in a lot of commercial applications. It is what the transducer inside of an inkjet printer head is made of. It can also be patterned into thin films for MEMS devices that research and things like that are doing, okay? It has a 3.3 piezoelectric coefficient of 15.1 coulombs per meter squared. And it has a Young's modulus of 110 gigapascals. Okay. So before we move along here, I want to talk about how this compares to other materials that we might be familiar with, right? So probably the most commonly used piezoelectric material is crystalline quartz. Crystalline quartz piezoelectric coefficient is significantly smaller than this, on the order of 0.1 coulombs per meter squared. And its Young's modulus is larger, on the order of 120 to 170 gigapascals. So PZT4 is about the best material that you could use for piezoelectric actuation in a MEMS device, because it's got a large piezoelectric coefficient and a relatively small Young's modulus, right? So if we want to achieve a 50 nanometer displacement, what voltage would we need? Right? So if we rearrange our equation, our voltage is just going to be equal to our Young's modulus times our desired displacement divided by our piezoelectric coefficient. And we would get 364.238 volts. So we have to apply 360 volts across a sample of PZT4 to get a displacement of 50 nanometers. That is an appreciable voltage. Not a lot of people have access to that, okay? So what can we do to generate similar displacements using smaller voltages? We can make stacked actuators, okay? So effectively, if I take, let me draw here just a stack of electrodes. Like so. Between each electrode is a sample of our material, and then I electrically connect them like so. There's our applied voltage. Now I am essentially distributing my displacement over multiple actuators, so that my total displacement should just be N times E33 over E. I wrote H there, but that has to be B. Let me double check here. Yeah. Why PZT is so great at this is because we can pattern thin films out of it. So we can put down an electrode, put down some PZT, put down another electrode, put some more PZT on over and over and over again. And the overall thickness of our thin films isn't too important in these particular applications. We just need to make sure that it's a reasonable overall thickness or reasonable number of layers to get our desired displacement. All right, so now let's talk about force. So we can look at what's happening here in a slightly different perspective. Yes. The number of transducers. Yeah, in this case, yes. Yep. So we have a piece of material and it is being elastically deformed. So we can effectively think of this as a non-piezoelectric material that is being stretched in a particular direction by this piezoelectric effect. Okay, so Hooke's law, F is equal to kx, right? We have a material undergoing extension. What's our spring constant? Young's modulus times the area divided by the distance in the direction of stretching, right? So that's going to be EA. In this case, we're going to be looking, since we're stretching in the 3 direction, this is going to be A3. H. And our X in this case, we are extending the length of our spring. So that's just delta H. Well, delta H over H is our stress. No, it's our strain, excuse me. And we know that our strain is, so we have A3. We're going to have E33 times our field in the 3 direction divided by our Young's modulus. These cancel each other out. And so this is going to look like E33 A3. Our electric field strength is nothing more than our applied voltage divided by our thickness. And this is the force generated by our piezoelectric actuation. So let's say that we're dealing with the exact same actuator we had a moment ago. It has an area of 16 millimeters squared and a height of 1 millimeter. What would the force be that we are generating by creating a displacement of 50 nanometers? Our force is just going to be E33 A3 V over H. So 15.1 coulombs per meter squared, 16 millimeters squared, 364 volts. Is it 364? Oh, yeah. Over 1 millimeter. This will come out to be 88 newtons. Because we are stretching a material that really doesn't like to be stretched a whole heck of a lot. That's why it took so much voltage, right? We can generate pretty large forces with piezoelectric actuators. This is the probably biggest benefit. All right, so that is what longitudinal actuation looks like. Transverse actuation is roughly the same thing, but there is an important difference here. Okay. So let's go to the next page. So under transverse actuation, we have a similar constituent equation. Now our stress in the one direction will be E times our mechanical strain minus E31 times our field in the three direction. If we are free to deform, T is equal to 0 again, giving us ES1 will be equal to E31 times field in the three direction. Rearranging this, our stress, in this case, it's going to be delta L over L will be equal to E31 times our field in the three direction divided by our Young's modulus. And from here, our induced displacement is E31L over EH times our applied voltage. Right. So now we do have a presence of the geometric properties of our transducer influencing our displacement, right? So how do we maximize our displacement? We make sure that L over H is really large. We make really long actuators. We can derive a piezoelectric force for this type of actuation as well. So we'll have, once again, Kx, where K is effectively our material's spring constant undergoing extension. X is just a dummy variable here I'm using for the displacement that we are trying to get. So this is going to be E times A1 over L times delta L. Since delta L over L is simply F1, we have EA1 times S1. Substituting in our relationship for S1 up here, we have E times A1, E31, V over E times H. Our E's cancel out, so we have E31A over H times our applied voltage is our piezoelectric force. So this is the force generated outwards as opposed to the force generated. That is piezoelectric actuation in a nutshell. All right, so I don't have anything else prepared for today. So what I'm going to go do is get some chicken strips and eat lunch. And then I am going to finish writing you guys' exam. And then I hope to have it up before I leave at 5. But it will definitely be up before midnight tonight. And it will be due by midnight next Friday. So you'll have 1 week to do this one problem, which I think is a reasonable amount of time because I strongly think you should be able to do it in less than an hour. 1 week to stare at it, or 6 days and 20 hours to stare at it, and then 4 hours to really do it. You can't stack, yeah, if you're just making it longer.
Yeah.
Which, yeah. So yeah, you can only stack for vertical displacement. All right, I honestly have no idea what I'm going to talk about on Monday, so we'll both be surprised.